The year is 2068, and low Earth orbit is dying. It's not happening all at once, but the decay is entirely visible. Every week, ground control logs more collision alerts. Every month, another dead satellite is lost to a high-speed debris strike. This is the reality of Kessler Syndrome, a runaway chain reaction where each collision creates more shrapnel. As the risk multiplies, the financial toll follows, with insurance rates for new launches tripling across the board. The physical toll on human outposts is even more severe. Crewed stations have to perform evasive burns so frequently, dodging incoming shrapnel, that crews joke they orbit in zigzags just to survive. Early proposals suggested we just sweep it all up, but the math quickly shuts that down. There are simply too many fragments, moving at tens of thousands of miles per hour, making a complete sweep physically impossible. Humanity shifts from panic to a structured defense through the Orbital Restoration Program. This project unites the engineering resources of 80 nations, creating a single global command for space traffic and debris removal. This effort requires abandoning an old assumption. We have to stop treating orbit as an empty vacuum and recognize it for what it has become, a collapsing natural ecosystem that requires active restoration. Before you can fix an environment, you have to map it. Humanity's first step is building a planetary nervous system called the orbital mesh. The mesh is a network of radar arrays and optical telescopes distributed across Earth and space. AI systems track every piece of junk, assigning a live trajectory, risk score, and collision tree, color-coding the danger level. The mesh then highlights the cascade nodes, the 100 massive dead objects triggering chain reactions. Removing these targets eliminates the conditions for orbital wildfires. Take an abandoned upper rocket stage, like this massive cylindrical bulk tumbling out of control. If a small piece of shrapnel hits a fuel tank of this size, it instantly splinters into thousands of new lethal projectiles. To neutralize these primary threats, engineers deploy orbital reclamation vehicles, or ORVs. These are specialized spacecraft built specifically to hunt and dismantle high-risk targets. The Harpoon-class ORV operates with brutal efficiency. It approaches a tumbling wreck, fires a tethered anchor into reinforced sections of the dead hardware, and uses vector thrusters to arrest the chaotic spin. By focusing exclusively on these heavy cascade nodes, the cleanup stops being an unwinnable battle against millions of tiny fragments and becomes a highly calculated surgical strike against orbital decay. But the largest objects are only half the threat. The most insidious danger comes from millions of microscopic fragments, pieces too small to physically grab, yet moving fast enough to punch through armored hulls. To handle this, we deploy aerostatic plasma swarms. These are dare-pleat-sized microsatellites flying in coordinated formations through specific, heavily polluted orbital bands. These swarms act like sheepdogs for shrapnel. They ionize the thin local plasma to create temporary electrostatic fields, subtly increasing drag to nudge dangerous millimeter-sized particle streams into decaying grave corridors. For fragments that the swarms miss, ground and lunar stations operate the photon momentum array network, universally known as the Broomlight system. These lasers do not vaporize their targets. Instead, a synchronized beam strikes a jagged piece of metal and gently slows it by fractions of a meter per second over repeated passes. It requires immense patience. One pulse of light does absolutely nothing, but 10,000 precise pulses over 6 months will eventually force a lethal fragment into a safe re-entry trajectory to burn up in the atmosphere. These microtherapies succeed because they don't try to catch every speeding bullet. They tame the chaos by subtly altering the physics of the environment itself. All of this engineering, however, is just a temporary bandage if we continue treating orbit like a landfill. To prevent a relapse, a new manufacturing mandate is strictly enforced. Every single spacecraft launched must now be built to be returnable, serviceable, or safely consumable at the end of its lifespan. And the derelict satellites we do capture are no longer viewed as waste. They become valuable ore. Automated orbital foundries capture this metal, using zero-gravity smelters and fabrication lines to recycle it. The economics of this transition are driven by gravity. Since it costs thousands of dollars to launch every kilogram of material from Earth, the millions of tons of refined alloys already in orbit are the most valuable resource in the solar system. Using this debris as feedstock for 3D printers, eliminates launch costs entirely, turning a billion-dollar cleanup bill into a self-sustaining manufacturing sector. The technical solution is secured by the Low Earth Orbit Preservation Accord. This treaty moves space operations out of the era of unregulated expansion and into a framework of strict environmental accountability. This treaty classifies debris creation as an environmental crime, mandates that all operators fund their own cleanup architecture, and permanently declares orbit a protected global commons. This chart shows the historical volume of orbital debris. After decades of exponential growth, you can see the exact year the line peaks and definitively curves downward. For the first time in a century, the total volume of debris in orbit begins to shrink. Overcoming Kessler Syndrome doesn't end with a giant explosion or a dramatic battle. It ends with the quiet realization that humanity has finally matured, transitioning from reckless exploiters of a frontier into permanent stewards of the sky.